the ethene molecule, carbon forms bonds by using sp2 hybridization. sp2 hybrid orbitals are formed from 2s and 2p orbitals. This leaves 1p orbital unhybridized. The hybrid orbitals lie in one plane, directed towards the corners of an equilateral triangle. The remaining p orbital is perpendicular to this plane. Each of the four orbitals is occupied by a single electron. Head-to-head overlap of the sp2 orbitals of two carbon atoms gives rise to a carbon-carbon sigma bond. The remaining sp2 orbitals overlap with the four hydrogen 1s orbitals to form four sigma bonds. In this arrangement, the remaining unhybridized p orbitals of the carbon atoms are close and parallel to each other. They can overlap in a side-to-side manner to give the additional p bond between the carbon atoms. The carbon atoms in ethene are linked by a double bond composed of one sigma bond and one p bond. If we tried to rotate one CH2 group about the other along the axis of the carbon-carbon bond, one of the p orbitals would also rotate. As a result, the p orbitals of both carbon atoms would not remain parallel to each other. Rotation would require the breaking of the p bond. For this reason, rotation around the double bond is restricted and the ethene molecule is planar, with all bond angles close to 120 degrees. Notice that the sp2 hybridization concept explains not only the geometry around each carbon atom in ethene, but it predicts the planarity of the molecule too.